His name should be written into the history of modern rail. It was erased instead. In 1908, an Italian professor named Giuseppe Belluzzo built what should not have been possible: a working steam turbine locomotive designed to make every piston engine on Earth obsolete. It ran. It produced 260 horsepower on the tracks outside Milan. The engineering press called it a leap forward. And then silence. Total silence. The man who invented the turbine locomotive died forgotten, and the reasons why say more about progress than any success story ever could. By 1908, the heart of railway power was still the piston-driven steam locomotive, a machine both celebrated and resented by railroad engineers. Every journey began with the same ritual: oiling the rods, checking the valve gear, and bracing for the relentless pounding that echoed through the rails. Underneath the spectacle of churning wheels, an invisible war was being fought against the laws of physics and the limits of Victorian engineering. The numbers were impossible to ignore. A typical mainline locomotive demanded nearly 50 hours of maintenance for every 1,000 kilometers traveled. Bearings wore out, pistons cracked, and valve gear needed constant adjustment. Each mile cost more than just coal. It ate up labor, steel, and time. Fuel consumption was staggering. In the early 1900s, railway companies reported burning through 85 kilograms of coal for every 100 kilometers, a figure that barely budged, no matter how much boiler pressure was pushed or how carefully the firemen stoked the flames. But the real enemy was hidden in the pounding rhythm of the pistons. As the wheels hammered the rails, a force known as hammer blow shook the track bed. Engineers measured these impacts in tons. And on a fast passenger run, a single driving wheel could deliver a shock of over 2,000 kilograms to the rails with every revolution. The result was a cycle of track damage, derailment risk, and expensive repairs that grew worse with speed and power. Railway boards complained that the cost of track renewal had doubled in a decade. The 1908 issue of The Engineer warned that further increases in boiler pressure no longer brought meaningful gains in performance. The engines were running up against a wall. Thermodynamic losses compounded the problem. Reciprocating engines wasted much of their steam's energy as heat, bleeding efficiency with every stroke. Even the best piston designs struggled to convert more than 10 or 12% of the boiler's energy into motion. The rest vanished into the air, billowing from the exhaust in clouds that signaled wasted fuel and lost opportunity. The industry's answer was to build bigger, heavier machines, more cylinders, higher pressures, longer boilers. But each step forward brought new problems. Heavier locomotives meant more hammer blow, more track damage, and even greater maintenance costs. The cycle was unsustainable. Railway managers grew desperate for something smoother, more efficient, less brutal on both men and machinery. The search for a better solution became urgent, a matter of economic survival as much as engineering pride. In boardrooms and workshops across Europe, the question grew louder. Could the relentless violence of the piston be replaced by something cleaner, quieter, and more reliable? The answer, some believed, might lie in the continuous rotary motion of the steam turbine, a technology that had already begun to transform ships and power plants. But on the rails, the piston's grip remained ironclad, and the cost of failure was measured not just in lost money, but in shattered reputations and forgotten names. Giuseppe Belluzzo entered the world in Verona in 1876, growing up as Italy's factories and railways reshaped the landscape. By 1898, he had earned his engineering degree from the Polytechnic University of Milan, a credential that marked him as one of the country's brightest technical minds. Rather than linger in academia, Belluzzo went straight to the railway shops of Milan, learning from seasoned engineers who measured progress in soot and sweat. This blend of rigorous study and hands-on work gave him a rare authority, someone who could speak both the language of equations and the dialect of the shop floor. Beluzzo's ambitions quickly outgrew routine repairs. In 1909, he filed United States Patent 931986A, titled Elastic Fluid Turbine. The patent's opening lines, written in his own careful script, set out a clear goal: continuous, uniform delivery of power with minimum pulsation, thereby reducing stress on the transmission elements. The diagrams were meticulous, each line revealing a mind that saw no divide between theory and practice. Beluzzo's turbine was more than a technical curiosity, it was a direct challenge to the piston-driven engines that dominated railways, engines he saw as wasteful and violent in their motion. His frustration with the old ways ran deep. Piston engines hammered relentlessly, shaking carriages and wearing out rails. Beluzzo believed turbines could offer something better: smooth, efficient movement, less wear, more reliability. His early patents, filed in both Italy and the United States, sketched out compact, high-speed rotors designed for real-world use, not just laboratory demonstration. The technical community took notice. By 1912, university records show Beluzzo had risen from assistant in 1899 to full professor at the Polytechnic University of Milan, a rare feat for someone in his 30s. Despite academic success, Beluzzo never settled for theory alone. Letters from this period, preserved in university archives, reveal a man impatient with tradition. He argued in lectures and correspondence that the future of rail power depended on boldness, on replacing the old with the radically new. For Beluzzo, the turbine was not just an improvement, it was a reimagining of how energy could move machines. By the late 1900s, Beluzzo had gathered enough support to move from blueprints to construction. The optimism in his writing is unmistakable, a belief that the turbine locomotive could sweep away the limits of the past. Yet he understood the stakes. Failure would cost more than a machine. It would threaten his career and the very idea that vision could overcome convention. Beluzzo was ready to risk everything, convinced that engineering genius could break the iron grip of the piston. Steam turbines dazzled engineers with their promise: silent, smooth, and nearly free from the pounding violence of pistons. But the railway was not a ship, nor a power plant. The challenge lay hidden in the numbers. A marine turbine spun at 6,000 revolutions per minute, generating power efficiently at high speeds. Locomotive wheels, by contrast, needed to turn slowly, about 750 revolutions per minute at full speed, and far less when starting a heavy train. The heart of the problem was mismatch. Turbines thrived on speed, but trains demanded torque, the raw, turning force needed to haul steel and cargo from a dead stop. Without adaptation, a direct-coupled turbine would spin the wheels so fast they'd tear themselves apart, or worse, fail to move the train at all when starting from rest. Beluzzo understood this from the outset. His patent drawings sketched out a solution borrowed from shipyards: reduction gearing. By introducing an 8-to-1 gear ratio, his design allowed the turbine to whirl at 6,000 revolutions per minute, while the driving wheels crept along at a manageable 750 revolutions per minute. This gear set, compact yet robust, was the linchpin, translating high-speed rotation into the slow, muscular push required by rail. The calculations were unforgiving. To deliver enough tractive effort, the gears had to absorb immense forces without shattering, while keeping friction losses low. Each tooth had to mesh perfectly, every revolution a test of metallurgy and precision. Beluzzo's notebooks from 1908 are filled with gear diagrams, torque curves, and handwritten equations, evidence of nights spent wrestling with the stubborn realities of physics. The reduction gear wasn't just a technical fix, it was a gamble. No European locomotive had ever relied so completely on a single, high-speed gear train. If it failed, The turbine concept would fail with it. But on paper, the solution seemed elegant, an alliance of speed and strength, promising to finally break the cycle of hammer blow and wasted energy. The workshop was ready. The next step would test whether theory could survive the heat and chaos of the railway. In 1897, Charles Parsons changed the course of engineering with Turbinia, a vessel that left warships trailing in her wake at over 34 knots. Her secret lay in a turbine, spinning at thousands of revolutions per minute, delivering a flow of energy so smooth and continuous that piston engines seemed instantly outdated. The Navy took notice. Soon, Parsons's turbines powered ocean liners and warships, where reliability and speed were not just advantages, but necessities. By the early 20th century, stationary turbines in power plants were achieving thermal efficiencies above 30%, a benchmark piston engines could never reach. Fewer moving parts, less vibration, and a steady rotary drive meant turbines transformed steam into motion with remarkable efficiency. Beluzzo watched these developments with the curiosity of an inventor searching for the next leap. His notebooks from 1907 brimmed with calculations, steam flow rates, blade angles, and the ratios that let turbines spin propellers at high speed while keeping ships steady. Parsons' success was more than a technical feat. It was a signal that a new kind of power was possible. If turbines could drive ships across oceans, why not trains across land? The promise was clear. Turbines offered continuous rotary power, doing away with the hammering and wasted energy of piston locomotives. The efficiency numbers from marine and stationary turbines, above 30%, hinted that steam's story was far from over. Beluzzo imagined a locomotive freed from pistons, powered by a high-speed rotor and reduction gear, blending the confidence of shipyards with the precision of power stations. The logic was compelling. Adapt what worked at sea and in generator halls to the rails, and the rules of railway engineering might change forever. For a moment, it seemed the relentless drive of the turbine could finally outpace the old piston, promising a future where power flowed in one smooth, unbroken stream. Inside the Officine Mécanique workshops, the air shimmered with heat and the scent of oil. Beluzzo stood among machinists and fitters, sleeves rolled, hands blackened from graphite and grease. The conversion began with the bones of an 1876 060T shunting engine, its old driving axle removed, frame braced for new weight. 4 axial flow turbines, each housed in a cast iron shell, took shape on benches lined with blueprints and calipers. 2 turbines per side were bolted to the outside of the boiler, each connected in sequence by thick, flexible pipes that would carry steam from one to the next. The ledger from Officine Mécanique records the delivery of these turbine housings in March 1908, each weighing nearly 180 kilograms. The boiler itself was transformed. At the rear, a new steam dome rose above the barrel. Its height increased by nearly 30 centimeters. An ungainly crown meant to steady the pressure for the turbine's relentless appetite. The dome's size startled even seasoned boilermakers, who grumbled that it looked more at home on a battleship than a locomotive. Inside, brass turbine blades were fitted with painstaking care. Each blade had to withstand the bite of high-pressure steam, spinning at speeds no piston engine could survive. The reduction gears, forged from hardened steel, waited on racks nearby. Their 8-to-1 ratio was the heart of Beluzzo's gamble, translating the turbine's dizzying revolutions into the slow, determined turn of a railway wheel. Chains and couplings designed to flex as the locomotive rocked and swayed linked the turbines to the wheels. Steam admission valves, 4 in all, were mounted boldly on the exterior, promising easy access but exposing them to every cinder and lash of rain. The workshop logbooks note the hours spent aligning gear teeth, checking tolerances by hand, and adjusting the fit of the dome. Tasks that stretched late into the night. By April, the machine stood ready, its profile unmistakable, a boiler bristling with turbine housings, the oversized dome gleaming above. Beluzzo watched as the last bolts were tightened, the promise of smooth, unbroken power now embodied in steel. The locomotive was ready for the rails, poised between hope and the unknown. May 13, 1908. The Milan test grounds buzzed with anticipation as the turbine locomotive rolled onto the track, its oversized steam dome gleaming under a pale spring sun. Beluzzo moved along the footplate, checking gauges and listening for the telltale whine of spinning blades. Officials from Ferrovie dello Stato and the Ministry of Public Works gathered along the embankment, joined by a cluster of journalists with notebooks ready. At the signal, steam surged into the turbine. The locomotive pulled away with a sound unlike any piston engine. There was no pounding, just a rising, continuous hum. The log entry from that day records a measured speed of 45 kilometers per hour and a continuous output of 200 horsepower. Acceleration was smooth, the usual hammer blow absent. An engineer's note from the test log reads, "No perceptible shock on the rails. The machine glides as if on oil." Crowds along the fence murmured in surprise, and the next morning, Corriere della Sera called it a spectacle of modern engineering. The press marveled at the absence of smoke and shudder, describing the locomotive as a promise of what rail travel could become. Yet even in triumph, a few mechanics exchanged uneasy glances, whispering about the unfamiliar gears and the challenge of keeping them running. For a moment, though, the future seemed to belong to the turbine and to the man who had dared to build it. In the weeks after the first public trials, the turbine locomotive returned to the workshop for what was supposed to be routine inspection. Mechanics opened the gear housings and found the beginnings of disaster. After just 150 hours of service, the reduction gears showed visible wear. Machinists recorded in the October 1908 log that the teeth needed to be remachined, a job rarely required so soon on any standard piston locomotive. Each pass of the turbine's high-speed shaft had left microscopic scars, the metal pitted and roughened by forces it was never meant to endure. The problems did not stop at the gears. Flexible steam pipes, meant to carry pressure from turbine to turbine, had begun to leak. By the third month, pressure drops reached 15%, cutting power output and forcing the crew to patch joints with strips of canvas and wire. The workshop ledger tells of repeated shutdowns to replace gaskets and retighten flanges, each repair adding hours to the maintenance tally. For the men tasked with keeping the machine running, optimism faded quickly. The numbers in the logbook were stark. Maintenance hours for the turbine prototype outpaced those of conventional engines, and every day out of service meant lost revenue. The promise of smooth, efficient power was being buried under a mountain of repairs. Even the most skilled fitters began to question whether the turbine's brilliance could ever survive the realities of the railway. Inside the Ferrovie dello Stato boardroom in June 1908, optimism gave way to calculation. The Finance Committee, faced with mounting repair bills and a growing stack of workshop reports, laid out the numbers in black and white. Their assessment, recorded in the official minutes, was blunt. The cost per horsepower exceeds that of proven piston locomotives by 45%. The statement landed with the force of a verdict. For every promise of smooth power and reduced track wear, there was the reality of expensive gears, custom-fitted steam pipes, and unfamiliar maintenance demands. The board compared capital outlay against the daily grind of operating costs. Turbine construction demanded specialized labor and new tooling, while the anticipated savings in fuel and track renewal simply failed to materialize in the trial balance sheets. A single line from the committee's summary captured the institutional mood. The turbine locomotive, though ingenious, cannot justify its premium in the present economic climate. With that, the experiment's fate was sealed. The board deferred any further orders, choosing instead to monitor conventional designs and the rising promise of diesel-electric power. The minutes closed with a final chilling calculation. The turbine's financial penalty outweighed its technical allure. In that moment, the dream of a new era in rail propulsion was quietly set aside, leaving its inventor with nothing but the echo of what might have been. Obscurity isn't just a fate, it's a verdict, handed down by the engines that win. Today, turbine technology drives super-fast trains across continents, while Beluzzo's name rarely appears outside old patent ledgers. Innovation's graveyard is crowded with visionaries lost to time, yet every leap forward borrows from forgotten minds. We still ride the tracks he once imagined, whether we remember him or not. Share your thoughts on invention and legacy below.